All right, welcome back everybody. Happy New Year. I hope you had a relaxing holiday. I had to a certain degree, but it's already gone. In today's lecture on pattern recognition, we will study all the k-means algorithms. And all is a bit of a euphemism, but at least 3 of them, actually I guess it's 4, I don't even know. Let me start with a disclaimer. I am somewhat of an expert on k-means clustering. That is a distinction I am not necessarily proud of, but let me tell you how it came to be. Who has not heard of k-means clustering? Okay, it's like, okay, basically most of you may have heard of this before. This is an algorithm for data clustering, which, clustering is an important step in many data analysis tasks. And it is by far the most popular approach to clustering out there. And almost everybody working in the field has heard about the k-means algorithm, or I should say the k-means idea. And there are numerous resources out there on the internet where you can download software that does k-means clustering for you. And all of this is okay, but the thing that turned me into a k-means expert is that a lot of people know about this idea, use it, but don't really understand it. Or don't understand implicit assumptions behind this approach to data clustering. And the real reason why I turned into an expert on this algorithm is that I once attended a scientific conference. It was not a conference on machine learning or a conference on pattern recognition, but it was a conference on computational intelligence methods. And I talked to one of the people there, got to talk, and talked about a problem they had been dealing with, and he told me that they had used k-means clustering, but it didn't work. And I was utterly shocked, because there is no situation where this will not work. The thing is that there are a lot of situations where the result that this produces are not reasonable or useful. And I thought up until then, this is about 4 years ago, I thought up until then that everybody working in the field was aware of the implicit assumptions in this extremely popular algorithm or approach to data clustering. It is so popular because it is so simple. And apparently because of its simplicity, many people do not bother trying to understand the underlying principles. And we, of course, will address all these underlying principles today. Here is what we are going to do in detail. So ever so briefly introduce you to the idea of data clustering. And then we jump right into this idea of k-means clustering. And everything I have said so far basically applies to Lloyd's algorithm. There are different algorithms we can use to accomplish k-means clustering, but if you were to do a survey among data scientists, whatever that is, for 99% of them, k-means clustering would be synonymous with this algorithm. We will also discuss other algorithms, and in particular, we will connect this idea of k-means clustering to a certain maximum likelihood problem. The great thing about the lecture up until today, lecture series up until today, is that we are by now well positioned to fully understand pros and cons, benefits and pitfalls related to this procedure. And I'll then summarize, and we are good. So yeah, I became an expert on k-means clustering. Like 4 years ago, I've been on a mission, a man on a mission, trying to convince the world out there that k-means clustering is more than this algorithm, and in particular that it does not apply to any kind of data you give it. Let's go. Do you remember a couple of lectures ago we talked about the idea of nearest neighbor classifiers, and I said that if we could come up with some way of classifying data according to a set of prototypes, and that is to say according to their closest distance to one of these prototypes, that this nearest neighbor classification implicitly creates a Voronoi tessellation of the embedding space, of the space, the data, the prototypes we are given live in, right? So for instance, with respect to this data point, every two-dimensional point in this two-dimensional sketch, once again, all the pictures will be two-dimensional, but this applies to higher dimensions as well. With respect to this two-dimensional prototype, every point inside this cell is closer to this point than to any other point shown in blue here. And in this sense, the shortest distances to these prototypes define these cells. In that sense, nearest neighbors create a space partitioning, or a more fancy way of saying that is a Voronoi tessellation. One of the questions we can ask is, well, you know, if we were given 1 billion such points, 1 billion of the blue points, and you know, some of them are rather close to each other, and if you have 1 billion of them, then there will be a lot of points rather close to each other, which is to say that some of the Voronoi cells will be rather small. And that is to say that if we were to do nearest neighbor classification with really a lot of prototypes, well, I don't know, would we really for some point over here, would we have to test against all of the points, or is there a way for us sort of to summarize some of these points into a single representative point? For instance, we might say, well, you know, these 6 points, or what is it, 7 points here, if we were to place a point here, they would create a different Voronoi cell, and that Voronoi cell would represent what's going on in this particular area of the data space we are dealing with. So a problem we could address is there a way for us to combine individual Voronoi cells into larger ones? Another fancy way for larger Voronoi cells is, are there some super Voronoi cells? And this question is, or these questions are fundamentally addressing the problem of data clustering. Now, what is clustering? This really is the most general thing we can say about clustering. If we're given a finite set X of stuff, patterns in our case, finite set, so that is to say there are just finitely many elements in this set, we might be interested in identifying structures within that set. And one way of thinking about structures is we might be interested in identifying groupings within that set. So for instance, this is a set, like the blue points indicate a set X, and yeah, I already said, you know, these 7 here, they are very close by. In a certain sense, they form a group. We can at least, you know, agree that this is not a stupid thing to say. And we can ask, you know, how many groups are in this set of blue points, and can we identify these groups? For instance, with respect to classification, if we could do nearest neighbor classification with respect to groups of points rather than with respect to individual points. So clustering is all about identification of latent structures, latent in the sense that it is there, but not immediately visible to us. We have to do some computation to identify those structures. And for today's lecture, I will confine our discussion to data sets that are subsets of the space Rm. So from now on, for the rest of today, data will be a collection of m-dimensional real-valued vectors. Right? Clustering is not confined to data like that. We can cluster words, we can cluster everything. Depending on what we are given, we may need different clustering algorithms, but basically there is nothing that would prevent us to cluster apples and oranges and bananas. Today, however, the stuff we are interested in are real-valued m-dimensional vectors. And another thing I have to say is that there are numerous different ideas as to how clustering can be done. And there are many different philosophies, like what kind of an approach should we decide for whenever we are looking for latent structures, groups of things within some larger set of things. Famous philosophies are, say, relational clustering. There are algorithms that are called spectral clustering or graph cuts and so on and so forth. Then there is this whole family of hierarchical clustering algorithms that can be done divisively or agglomeratively. Typically, the algorithms that do that do some sort of linkage computing. And note that I am not going into the details whatsoever. I'm just dropping these terms in front of you, right? Then there are density-based approaches. Famous algorithm here is dbScan. And the stuff we are interested in today is called prototype-based clustering. And by far the most famous idea there is this idea of k-means clustering. There are other ones, LBG and so on and so forth. But among all these different philosophies, really by far the most popular clustering algorithm or clustering approach of philosophy out there is this idea of k-means clustering. And we will focus on that today. Now, if there are so many different clustering philosophies, then of course we should ask, so what distinguishes them? Why are there so many different ones? And what are the differences between them? And are they clearly distinct? And the unfortunate answer is the distinctions between different philosophies of how to cluster data are not that clear-cut. Quite often they are really, many different algorithms are in the end the same idea, just approached from different angles. So distinctions or differences between clustering algorithms are often rather fuzzy. And at the very heart of it, differences between clustering algorithms boil down to how they answer these two questions. What defines similarity? And what properties should a cluster, a latent structure, or a subgroup of things within something larger have? And before I continue discussing how k-means clustering answers these questions, I once again thought this is probably a good time to point out once again that we have to be aware of the fact that clustering, that is this identification of groups within some larger sets, is in general an ill-posed problem. Right? In one of our first lectures, I asked you to cluster this set of 9 elements into 3 groups. And here we see that a fundamental problem of clustering is the question, what defines similarity. So we are given 9 elements here, nine entities, shapes, with different colors, different sizes. And if we say, okay, let's see if we can divide that into 3 groups. Well, the first one is apparently sort of a group like this, then a group like this, and a group like this. And here we have implicitly said, well, similarity is given in terms of shape. So we can think of, let's compute a feature from these things. For instance, a feature could be the number of vertices, right? So 3, 4, and 5. That would be a feature for these things. Now we have 9 numbers. Let's use these 9 numbers to group that into 3 substructures. And that would suggest that the first one is this, the second one is this, the third one is this. We could just as well compute a feature that would indicate size of things. And then we would end up with these 3 groups. Another feature could be color. And we would end up with yet another possible grouping. So clustering in general is what we call an ill-posed problem. And that is something you always have to be aware of, regardless of what I'm going to discuss from now on. It may not even work, right? So please keep that in mind. Now, K-means clustering is by far, and there is no discussion about this, the most popular algorithm for vector quantization. Remember that I said today the data objects we are interested in will be m-dimensional real-valued vectors. We're given data like that. K-means clustering is hands down the most popular algorithm or philosophy to do that. And that is because it is such a simple and intuitive idea. What it does is, like if we're given a set X of data, it determines K subsets. And these subsets, I call them CI for cluster I. And the number K of subsets we are typically interested in is typically much, much smaller than the number of data we are given. Right? If we are given 1 billion data points, what would be the rational idea of clustering that into 100 million clusters? If we are given 1 billion data points, let's find 10 clusters. That's cool. Then we have, really done something about our data. So K, number of clusters, is typically much, much less than the number of data. And in K-means clustering, each of these clusters is a subset of X, of the data we are given. And in particular, each of these clusters, or each of these subsets, they are disjoint. If we compute their intersection, the intersection is empty. And the K clusters, if we compute their union, then they reproduce the X, the data we are given. This is how K-means clustering answers question 2. What properties should a cluster have? A cluster should be a subset of the data we are given. Any 2 clusters should be disjoint, and the union of all the clusters should represent the data we are given. And here is how it answers question 1. What defines similarity of data points? What K-means clustering does is it says that for every cluster Ci, there is a prototypical vector. And I will call this vector mu I. So K-means clustering implicitly represents every cluster, a subset of data points, in terms of a single vector. And then the definition of a cluster is that cluster Ci consists of all the data elements in that set X we are given that are closer to mu I than to any other of these cluster prototypes. That is what defines similarity here. It is defined in terms of Euclidean distances to prototypical data points or elements. I should not say data points, but I should say similarity is defined in terms of distance two prototypes. And if two data points, say x1 and x2, are closer to mu I than they are to mu L, that means that they are more similar than, I don't know, a data point x3 that is closer to mu L than to mu I. This is how k-means clustering answers these two crucial questions. And if we look at this, this is, of course, this nearest neighbor thing in disguise. Here we are dealing with the problem of computing distances to certain prototypes, and that is, of course, to say that k-means clustering produces a Voronoi tessellation of the data we are given. And in that sense, it does, it sort of computes super Voronoi cells. If we have some prototypes, say over here, then all these 7 points would be part of this cluster, and that would have a certain Voronoi cell. And this is then to say that the problem at the heart of k-means clustering is to come up with these k prototypes, mu1, mu2, up to mu k. And then there's, of course, the question how to do this, how to determine these k prototypes for the k clusters. And given everything we have discussed up until today, it would appear as if it was a good idea if there was some objective function we could minimize, such that if we find a minimum of that objective function, that would correspond to good cluster centroids. Very abstract idea. Let's look at this in detail. So we could say the thing we want to minimize is the distance between points xj in a cluster Ci with respect to the prototype mu I of that cluster. And of course we have k such prototypes. That is to say, if we can sum these distances within every cluster and then sum that over all the clusters, and if this objective function k sort of indicates the number of clusters, if that is a small value, then we define that to be a good choice of these mu I. Right, so this is an objective function, and given what we discussed up until today, it seems always a good idea to sort of minimize or maximize these objective functions. Here it's about distance, it's always a good idea to minimize that. We are interested in finding k such prototypes. We need some criterion that would tell us whether or not these prototypes are any good, and this is the criterion we impose. We say, okay, let's find k such prototypes that this expression here becomes as small as possible. Right? And once again, let us just assume for a second we already had them. Right? We have these k prototypes, mu1, mu2, all the way up to mu k. We have them. And of course, given all the data we have, we can now sort of compute for every data point what is the closest prototype. So we can have this assignment of data points to prototypes. We can compute how far away is this data point from its closest prototype. Can look at the sum of all these distances, and then we sum that for we sum these distances between a data point and its prototype. We sum that over all the data points in that cluster. And then we sum that over all the classes, and that total sum, this double sum, should be small. If the mu I are chosen such that this is small, then we declare this to be a good solution for our problem. All right? And let me briefly discuss this representation here. I hope you can understand what this means. Like, say we are given these things, and every of these prototypes defines a cluster. When x, some number 3 is closer to mu5 than to any of the other mu's, then x3 is in cluster 5. Right? So we can determine the data points that belong to a certain cluster. And then once again, we consider for every data point in that cluster the distance to the prototype of that cluster. We want to minimize this double sum here. Instead of saying xj in cluster Ci, could replace this summation here by this crazy summation. Here we sum explicitly over all the data points in a certain cluster, and here we actually sum over all data points from 1 up to n. So this is a computationally, this is a larger for loop if you want. And of course here we first have to determine does xj belong to Ci, but then say in this cluster there are only 10 elements, so this would be a sum over 10 things. And if this n is 100,000, then this would be a sum over 100,000 things. So that looks, like more effort, and it certainly is. But this one is nicer to be dealt with mathematically. And look at these Zij here. Those are indicator variables. They indicate if xj is an element in Ci. If that is the case, then this would be 1. If this is not the case, then this would be 0. So therefore this is exactly the same as this. Because if xj is not an element of cluster mu I, then this will be 0. So this will not contribute to the overall sum here. We will add some zeros, so that's okay. But if xj is an element of mu I, then this will be 1, and that will actually contribute to that sum. So if you have not seen this idea of indicator variables before, I discuss it in a couple of the other lectures as well. If this is baffling to you, please sit down at home and convince yourself that this here is indeed the same as that, given that these factors are defined as this. Okay? Now, given that we have defined this objective function for k-means clustering, then of course we now have to minimize it with respect to a choice of k such prototypes. And even though these two formulations of this objective function look rather simple and are really very intuitive, right? We are looking for prototypes such that the distances of the data to their closest prototype summed over all the clusters is as small as possible. It's a very intuitive idea. Minimizing that is a surprisingly hard problem. It is actually NP hard. There is no algorithm known today that in a general setting, general dimension m, general number of data n, is guaranteed to find the optimal solution. It does not exist. We do not know that yet. K-means clustering is NP hard. I am not going to prove this in this lecture. But this is the first important thing you need to know. This can, in general, not be solved. Or we do not have any guarantee that the solution we find by minimizing this objective function is the best we can get. Any available algorithm that minimizes this objective function is but a heuristic. And this is different, for instance, in comparison to when we discuss these least squares method. There are squared distances here, so it looks like a least squares problem, but it is not, because we have this double sum here. And in least squares optimization, we know that there is a unique minimum. And therefore, we can think of how to get it. But here, there is no such thing as a unique minimum, and it is therefore not really clear how to find the best minimum. Any algorithm that minimizes this k-means objective is a heuristic. Okay, then let's talk about k-means clustering. But let me be precise, let's talk about Lloyd's algorithm for k-means clustering. And this is the second important thing you need to take away from today's lecture. 99% of all the texts you read about k-means clustering say, this is k-means clustering. Lloyd's algorithm is synonymous with k-means clustering. Why? Because it's incredibly simple. We'll see in a second why it's so simple. It appears as if this is synonymous with k-means clustering, but there are many other algorithms and we'll discuss them. How does this one work? Well, we are given the data in X, and the task is to find suitable prototypes. This algorithm begins at some iteration t equals 0 by randomly selecting k points. And I should say randomly in quotation marks. It's actually dangerous to do that totally randomly. There's a lot of research going on how to initialize this algorithm. But let's say, for the sake of the argument, we randomly initialize these prototypes. And then we begin an iterative process. The first thing we do in each iteration is to say, okay, now given these prototypes, we can of course compute the clusters, because we discussed that the cluster is defined as the set of data points in X that are closer to a certain prototype than to the others. Right? So we can, given the prototypes, definitely compute clusters. Now, in the next step in this iteration, we can say now that we have computed the clusters, is there a way for us to improve on our prototypes? And it turns out a very good idea with respect to these Voronoi tessellations, and this is what k-means clustering does. It computes Voronoi tessellations. A very good idea with respect to Voronoi tessellation is to set the prototype of each cluster to the mean of that cluster. This is where the name k-means comes from. Right? The prototypes, so far I have talked about them as prototypes, but these prototypes are in fact the mean vectors of the collection of vectors assigned to a cluster. So k-means clustering updates the means, then increases the iteration counter and continues with this process. Now we have new means, we compute new clusters. Now we have new cluster, we compute new means, we compute new clusters, we compute new means, we continue this until this converges. How would we know that this has converged? There are different things we could test for. First of all, this is what I prefer. We could see if the assignment of data points to clusters does not change anymore. Right? If in the current iteration we get exactly the same assignment of x, of all the x to the corresponding clusters as in the previous iteration, well then I guess we're done. Another idea to test for convergence could be to say, well, let's see if these cluster means are not changing anymore. If the current mean is not that far away from the last mean for every cluster, and not far away, let's have some threshold epsilon there, like some variable that would indicate what is close enough. Or it can also happen that this algorithm happily runs for a very long time, and because it's an NP-hard problem, it's just a heuristic, and maybe our initial choice of centroids was really unfortunate, and cluster assignments continue to change and maybe even to flip around or whatever. Let's stop this after 100 iterations, or after 1,000, or after 1 million. Right? So these are three things we could consider as convergence. Right? But of course there are many other things you could test for, and if corresponding conditions are true, you could declare victory and say, okay, this algorithm has now finished, and let's look at the results. Here is an example. Those are a couple of data points. It's actually, those are the data points we are going to consider today. And apparently there are, 3 clusters in here, right? So we can see that. What I did here is I randomly initialized 1, 2, 3 centroids. So the squares are the centroids or means, and here I'm showing the ones I used to initialize this algorithm, right? And then in the first step within this loop, we have to compute the clusters. And every point shown in orange is closer to this mean than to the other 2. Every point shown in purple is closer to this mean than to the other 2. And every point in green is closer to this mean than to the other 2. So this is the situation after the initialization. And then we update the means, and that is to say, for instance, with respect to this purple cluster here, this original mean is definitely not the mean vector of all the purple points. That would be here, right? So we update this centroid to somewhere over here, and update this centroid to, I don't know, somewhere over here, and this one somewhere over here. And then we recluster, that is, we reassign all the data points to their closest mean, and we get this. And in this silly example, that actually terminates after 4 iterations. And this is the result we get upon termination. And that looks good, in the sense of, yeah, the algorithm has exactly identified those 3 groups within the data. Everybody in this room would have called a group within the data. Okay, so seems to work. Great. We then need to ask, well, will this ever converge? I mean, are we guaranteed that this will converge? Or are we guaranteed that every iteration of this algorithm will improve on our objective? That is the question we need to ask. When I ask, will it converge? What I implicitly ask is, will every iteration of Lloyd's algorithm improve our objective function? And it does. We note that the mean of cluster Ci is actually the arcmin over all y, all the x in cluster Ci minus y squared. If we were to solve this expression for y, if we are to look for that y that would minimize that expression, that would exactly be the cluster centroid mu. And that is to say that this update of the means cannot increase the objective function. Right? That is to say that within this loop here, these steps will never increase the value of E. They may produce exactly the same value of E if this does not change anymore, but typically they reduce it, but they can never increase it. It's impossible because of that property of the mean. And we also note that by design, and this is how we define clusters. A cluster is the collection of points that is closer to a certain mean than to all the other means. That by design, Lloyd's algorithm cannot increase the value of the objective function in equation 4. Like when we do this assignment of data points to clusters, this by design cannot increase the value of the objective function. And this is a very loose proof, but these 2 statements boil down to the question that in every iteration, the new value of the overall objective will at least be less than the previous, less or equal than the previous value. Right? So every iteration will improve on the objective function. This does not say that it will ever converge, but of course in practice we stop that after, it can run forever, but we would stop it after, I don't know, some larger number of iterations. So in that sense, yes, this will converge to at least a local minimum of this objective function. Okay. And in today's lecture, I have a lot of assignments for you. Here is the first one. On the previous slide, I said we note that μi, the centroid of cluster Ci, is the minimizer of this expression here. And we note that, but I want you to make sure that this is really the case. Do that at home. Well, you don't have to, but I really would encourage you to do that. Given everything we have discussed up until today, everybody should be able to do that. Right? Treat it as a least squares minimization problem and have a look at the solution you get. Please verify that this is true. It's the first assignment I have for you. Now, the fact that this really simple algorithm, Lloyd's algorithm, which 99% of all the people believe is k-means clustering. It's almost synonymous with k-means clustering. The fact that we know that it will converge to a local minimum in the error landscape of this objective function says nothing about the quality of the solution we find at this local minimum. And the fact that we know that it has to converge eventually says nothing about how fast or quickly it will converge. Right? In practice, if we use this algorithm for where it is designed for, then that will converge quickly. Right? But that colleague of mine I met 4 years ago, of course, applied it to a situation where this algorithm should not be applied, and so it did not work according to him. Practice, if we use this idea of k-means clustering for data where we can know that it will work, this will work well. And later on today, we will see what kind of data it is where we know that it will work. Right? Nevertheless, I already said it, it really crucially depends on how we initialize these means. Right? If we do that in a manner that is not appropriate, the results will be very, very bad, and it may take a very long time for this to converge. And if you do not believe me, here is the second assignment. I want you to read this and to watch these 2 videos on YouTube. Right? They actually show, this one shows k-means clustering in action, like every step is shown individually. And this one shows, on an extremely simple example, if you have different initializations, you'll get different clusters. It's of course very unsatisfactory, but this is how it is. And therefore, I should say at this point, if you ever decide on using k-means clustering, and now I should say Lloyd's algorithm for k-means clustering, later on in life, run it a couple of times, not just once. With some initialization you get some result. Run it 10 times and look at which of these 10 results you will get gave the best objective value, and use those means you got for that run where the result was the best. You really have to run this simple, extremely popular algorithm several times in order to be sure that the results you get are reliable. Watch this video. This is baffling. This is baffling. Okay, now, basically, this is the point where most lectures on k-means clustering stop. Okay, so they would have discussed everything we've discussed so far, slightly more detail, but it's not worth it. We need to widen our perspective. And the important thing is that there are many other ways as to how we can minimize that objective function. Hardly anybody knows about them. Very unfortunate. And the next one we'll discuss is Hartigan's algorithm. Have you ever heard of Hartigan's algorithm? No, because nobody has. It is much less well known than Lloyd's algorithm. And the funny thing is that it is provably, we can mathematically prove that the results Hartigan's algorithm will produce are better than the ones produced by Lloyd's algorithm. That can be proven. It is sort of beyond what we can do in this course, but we can prove that. We also know that this algorithm we are going to discuss next will converge, and we also know that it converges quickly. So what is Hartigan's algorithm? Here we go. This is k-means clustering, but seen from a different point of view, right? Really, like 99% of all the people out there think that k-means clustering is Lloyd's algorithm. That is not true. This algorithm realizes k-means clustering. What does it do? We are given our data set, capital X, and for every element in this data set, at the beginning, we say, this is an element of cluster 5, this is an element of cluster 3, this is an element of cluster 5, this is an element of cluster 2, this is an element of cluster 1, this is an element of cluster 5, randomly. We do not initialize means, we initialize clusters. Randomly, totally randomly. We randomly assign every data point to any of the k clusters we have. And once we have the clusters, we compute the means, right, using the mean updates we've seen earlier. And then we enter a loop. And this is just, we enter a loop. And in that loop, we iterate over all data elements again. And for every data element, we look at, okay, what is the cluster it is currently assigned to? Let's call it, I don't know, say xj is currently assigned to ci. We then remove xj from that cluster and update the mean of that cluster. Now we have removed one element, right, that has consequences for what is the actual mean of this reduced cluster now. We have to update the mean of this reduced cluster. We've reduced it by one element. So we remove it and recompute the mean of that cluster. And then we enter another loop, and I have hidden this in mathematical jargon here. Now we have the k clusters and an element that is floating around. And what we now do is we assign it to cluster 1, compute the overall error, like this overall value of the objective function. Then we assign it to cluster 2, compute the overall value of this objective function. Then we assign it to cluster 3, compute it, and so on and so forth. And once we have tested it, what would happen if we assign it to this cluster? What would happen if we assign it to that cluster? What would happen if we assign it to that? Once we have tested this with all the clusters, one of them, like one assignment, or what would happen if we assign it to cluster 5, say that was the best, produced the best overall objective value. So once we have tested it with respect to all the clusters, we have identified the assignment of xj to any of the clusters that gave the best overall objective. And so we say, okay, let's put it there. Because if we put it there, the overall error was smaller than if we put it here, or if we put it there, or there, or there. This is what this means. So here we have all our k clusters, and this is to say we extend one by one. With this element we have taken away from cluster ci. And so we have to do this with respect to all of them. So first we add it to cluster C1, compute the overall error. Then we remove it from cluster C1, add it to cluster C2, compute the overall error, remove it from cluster C2, and so on and so forth. Right? So we determine the cluster for xj, that if we were to put xj into cluster, say CW for winner, that would give the best overall result. Well, if we do this, and the assignment of data points to clusters does not change anymore, then we are done. If it still changes, then we have to continue with this crazy, let's remove it from a cluster, let's test what would happen if we assign it to the other clusters, and so on and so forth. This is called Hartigan's algorithm for k-means clustering, and here is how this looks like. So at the beginning, I have randomly assigned data points to clusters. This is like totally random, right? And so therefore the three means of these three clusters in this, I have set k to 3, are somewhere in sort of like the center of these three groups of points. And after we have done one such for loop, and by for loop I mean this one, right? After we have done this once, the situation looks like this, and there is still one mistake. So this green thing here should not be green. So we have to do it once more, and this is the result after 2 for loops. So this converges after 2 iterations. All right. And the thing, when I said we can prove that it gives better results than Lloyd's algorithm, is to say that we can prove that this algorithm will not be so likely as Lloyd's algorithm to be trapped in local minima. This one is mathematically guaranteed to find better minima of the objective function. Watch this. This is a video that shows Hartigan's algorithm in action. Every step is shown in that video. There's nothing for you to read because I actually want you to implement that in the next project. You have a question?
Yes, maybe the previous slide.
This one? No.
Yes, this one. Here, I think the main difference with this algorithm and the Lloyd algorithm is just the initialization, what we do. Other than that, it's still we are actually minimizing the error.
Oh yeah, we're definitely minimizing the error function. That is for sure, right? Because this is what, like here we are minimizing the error function.
Yes.
Right? But we are using a totally different philosophy.
Yeah, initialization has a very different way.
It is, yeah. I mean, of course, the initialization is different, right? But here we note that what we are doing here is not here. This is actually a cluster assignment, right? But this cluster assignment is not with respect to closest distance to a prototype. We really just assign it to the first cluster first, then to the second cluster, then to the third, and so on, and then look at what was the assignment that gave the best overall result.
That minimum will still be the one we have the closest.
No, that's the crazy thing. That is exactly the difference here. It may happen that, and I cannot show you, I mean, because it is not, but look at this. This thing here is closer to that one than to this one. And still, apparently it happened that it was assigned to this one. So in some iteration of that algorithm, the assignment of this point, this green one, to this cluster here, gave a better overall objective than as if we would have assigned it to here. Of course, in the next iteration, that will be remedied. Right? But this is really, like here, the assignment of data to cluster is not based on distances, and this is why it is better. This is why it is better. This is why it does not cluster according to this Voronoi criterion. Of course, once it is converged, we have Voronoi clusters. But the clustering does not happen according to closest distance. It's really, we tested what would happen if it was a point of this cluster, what would happen if it was a point of that. It's computationally a bit burdensome, but much more robust than Lloyd's algorithm. Much more robust.
So when we say that the error is minimum after assignment, what we are actually comparing in that case? I mean, when we say that cluster point J is assigned to cluster Ci and the error is minimum.
Oh no, we don't say minimum. Like in every iteration we compute this overall thing here. No, the objective is a distance, but the assignment is not. Right? So, say xj has been an element of cluster 5. We remove it from cluster 5 and put it in cluster 1. We compute this. We remove it from cluster 1 and put it in cluster 2. We compute this. We remove it from cluster 2 and put it in cluster 3. We compute this. Eventually, we have put it in every cluster, have computed all these e's, and then we say, okay, when we put it in cluster 7, the e was the smallest. So let's put that x into cluster 7. But this assignment of x to the cluster does not depend on the distance to the centroid of cluster 7. Right? Of course, the evaluation, again, depends on the distance, but the assignment does not. Right?
Exactly based on all other clusters, considering all the
Exactly.
clusters.
And when you are going to implement that in the next project, you can do this very, very smartly, and then it will be very, very fast, or you can do it horribly stupidly, and then it will be horribly slow. And no offense, you really need to know how to do it smartly, and I would be extremely happy to see if somebody could come up with the way of how to do it smartly, but we'll discuss this once the projects are done. All right? I would expect, and this is no offense, and really don't be alarmed, if you are going to implement this, it may be very, very, very slow. But it can be done extremely fast. And we'll discuss that in the upcoming projects. Okay, Hartigan's algorithm. Ever so quickly, next one, McQueen's algorithm. What if there are really many, many data points, like billions of them, right? A lot of them. Or what if we are dealing with a stream of data points, right? Either like the data is so many that it does not fit into the memory of our computers, or it really arrives one by one by one by one, and it would take a very long time for us to wait until they are all there, but we have to make decisions sort of in an online manner. What are we going to do then? Well, the answer is K-means clustering can be done in an online fashion. And this is called McQueen's algorithm. And to see how that goes, I want you to note this. Right now, no cluster, just a set of points, x, x1, x2, x3, all the way up to xn, and their mean, right? So mu is 1 over n, the number of data we're given, sum over all the x. This is the mean of a set of n Euclidean vectors. And I'm using this superscript n here to indicate that this is the mean of n such vectors. Right? We can split this sum into two parts. And I'm doing this without loss of generality. You could sort of split it into whatever, but I split out the last one. So we can express this sum as 1 over n, sum where j ranges from 1 up to n minus 1 xj, plus 1 over n xn. This is obviously exactly the same as this, right? Now, but this here is somehow the mean of n minus 1 points, but the mean of n minus 1 points would have to be computed with a factor of 1 over n minus 1 in front of it. So in order for this here to be mu n minus 1, we have to multiply it by n minus 1. Can you see that? That this here, 1 over n, this sum, is n minus 1, this mean, divided by n. Okay? So the mean of n points can be expressed as a convex combination of the mean of n minus 1 points and a new point. Okay. And that is to say, means can be computed iteratively in an online manner. If your data arrives one at a time, you can use every new incoming data point to update your current estimate of the mean of a large number of data points. And here is some algebra, and I really don't have to discuss it. The thing is that we can understand the new mean as the old mean distorted by something, some shift into the direction of the new data point. This here is a vector that points from the old mean to the new data point. So we have a couple of data seen already. Here's our current mean. In comes a new data point. We slightly move our mean towards that new data point. Here's McQueen's algorithm. We begin by initializing the means again. This is not as in Hartigan's algorithm, this is rather like in Lloyd's algorithm. Here we initialize the means. And then there is this stream of data, or this extremely large set of data. And we iterate over it. for every incoming data point xj, we look for the winner mean or winner centroid. We are given k means at some point in time. In comes a new data point. One of the means will be closest to this new data point than the others. We declare the closest one the winner. Right, so we determine that mean out of our k means that is closest to the new data point. We call it the winner, and then we update this winner. So first of all, we say, okay, so this mu w, the winner here, will now be responsible for another data point. So it was responsible for some number of data points up until this iteration. Now we have seen that the new data point is closest to this mu, so it will now be responsible for yet another data point. So the number of data with respect to that has to be increased by 1. And then we update this winner centroid using the equation we had on the previous slide. We continue this. Either we are going to stop that eventually, and we can then use these means to, look, I've shaded it out here, use these means to compute clusters, or we could, at every iteration of this algorithm, update the clusters. I would hardly advise you not to do this. Let this run, and once it has seen all the data, compute the clusters at the very end. Okay, this is called McQueen's algorithm. You can read about it in these lecture notes, and here is a video that shows this algorithm in action. Look at it, it's baffling, it really works. And it works surprisingly well. Okay, and that leads us to the problem, when will this work at all? Right. And here is a data set of two-dimensional data points. And how many clusters are in there? 2, right? I mean, every conscious human being would say there is one group of points here and one group of points there. We cannot but see that. There is, they are there. So, I look at this data and I say, let's use k equals 2 means clustering on this. And this is what we get. And we'll always get something like that. We will never have k means clustering identifying this group of points as a cluster and this group of points. It will always look something like that. Of course, details depend on initialization. The blue one might be here and the orange, and then this one might be there. But it will always look like that in principle. And this is two-dimensional data, and there are obviously 2 clusters, so we set k to 2, and it doesn't work. What went wrong? You are right, and we have to make that precise now. In the situation on the previous slide, I have applied k-means clustering to a setting where I could have known in advance that it will not work. Right? And this is what most people do not understand. The algorithm will never crash. It will always do something, and it will always produce some results. But the results may not make sense. And then they tell me, yeah, it doesn't work. And this is not the fault of this philosophy of k-means clustering. It's the stupidity of the people who use it because they think that k-means clustering is synonymous with data clustering, and they also think that Lloyd's algorithm is synonymous with k-means clustering. And they have no understanding of what it is they do there. They download it from the web, run it, and tell me it does not work. And I am a man on a mission, and I have to tell you why it cannot work in this situation. All right. And that leads us back to maximum likelihood arguments and probability theory. And here is a way of thinking about what it is when we look at a data set that consists of certain subgroups, clusters. And I should say this is a model. This is, of course, not how data happens to be produced in reality, but conceptually we can think about it like this. Let me go back to this. I should have had you. Like here, we are given two-dimensional data. I don't know, it's with 150 points or so. And what I'm now going to discuss is a model, a theoretical idea for how something like that could come into being. Right? And of course, the model and theoretical idea I'm going to discuss is not how this would happen in reality, like some real measurements, I don't know, weight and height of elephants, weight and heights of tigers and stuff. But bear with me. This is the power of mathematics, that we can think about abstract ideas in order to talk about practical things. Now, we could say we are given a data point x of points. How could any of these points have ended up in this data set? We could say we randomly select a cluster. Very abstract. Really, this is not concrete yet. This is just abstract idea. We randomly select a cluster. We roll a dice and it says 5. So we say, okay, this new data point will be in cluster 5. Now then, if it is in cluster 5, where exactly will it be? We say, now given that it is in cluster 5, it will be produced with a certain probability, given that it is in cluster 5. Right? So, very abstractly, we assume that there is a probability for each of the clusters, that a data point is in each of the clusters. And once we sort of have decided it is in that cluster, there will be a probability for how likely it is given that it is in that cluster. This is called a generative model. Right? Because if we assume this idea that we sort of roll a dice and then it is in cluster 6, and then we say everything in cluster 6 is, say, normally distributed according to a Gaussian, and that is to say, okay, it's in cluster 6 that is over here, and then Gaussian distributed, which is like slightly more likely over here than over here. Right? That is a generative model. And from what we discussed earlier, we know that we can then express the probability of observing that particular xj in our data set could be understood as the sum 1 to k, the probability of being in cluster Ci, so I ranges from 1 to k, probability of being in cluster Ci, and then the probability for xj given cluster Ci. This is called a generative model, and again, a very theoretic idea. It's definitely not how things would happen in reality, but it's a mathematical way of thinking about how this collection of 150 data points could have been produced. Right? There we had like 3 clusters, so I want to add a new data point to these 150 points. I roll a dice, it says cluster 2, and then within cluster 2 say some normal distribution about the mean, so let's put it here. And I already said it. Let's assume, this is another modeling assumption, that within each cluster we are talking about a Gaussian, a multivariate Gaussian. So this conditional probability of Px given cluster Ci, that would be a multivariate Gaussian, right, with mean mu I and covariance matrix sigma I. And I really don't like to carry around this 1 over 2 pi stuff, blah, blah, blah. This is called gamma I now. Right? All the normalization is enclosed in gamma I. And let us simplify this idea of the multivariate Gaussian for every cluster. Let's say, you know what? Instead of having each cluster having their own covariance matrix, let's say it is the unit matrix for all of them. Right? So you know, it's like some multivariate Gaussian, different clusters, different multivariate Gaussians. But let's say, you know what? The shape of these Gaussians is all the same. Their covariance matrix is all the matrix with lots of zeros and 1 along the diagonal. And even the sigma, let's put it like the variance in every dimension. Let's say it's 1. And if we put the unit matrix in here, then this whole expression simplifies to this. Right? I want you, if you do not believe me, convince yourself. So this is now our model. Generative process. We randomly decide for a cluster, and within that cluster we decide for a location for that data point, and that will be distributed according to this very, very simple multivariate Gaussian. And that is to say, what we are doing here is we consider what is called a Gaussian mixture model. And in fact, the model we are considering is utterly trivial. So one of the most simple Gaussian mixture models we can conceive of. And of course, as always in probabilistic modeling, we can now sort of turn it around and say, here is an observation of data, and here is our model for what would explain the data, and that is to say we now have to adjust the model parameters according to the data we are given. And we have done that a lot of times, so let's go for it once more. The model parameters in this very, very simple Gaussian mixture model are of course only the mean vectors of those Gaussians, k Gaussians, and these weight vectors. Like this is my way of saying this Wi is the probability for being in a certain cluster. Did I make that implicit here? I did not. So here I'm writing P of Ci, and that will now be called Wi. It's easier to write down. Right. Oh, actually, here, there it is. Wi is the probability for being in cluster Ci. Okay. Maximum likelihood, no big deal. Here is the likelihood function. Of course, we assume that all the data have been produced independently, as always, very convenient assumption. So we have the product, where j ranges from 1 up to n, number of data points we are given, probability of observing xj. The probability of observing xj is now the sum where I ranges from 1 up to k, wi, and the corresponding normal distribution. Then we can take the log of that, and we have that this product becomes a sum, and then we have to take the logarithm of this sum. And for everything we have done earlier, there was no sum here. There was, say, just one normal, and then we had to take the logarithm of that Gaussian distribution as e to the something, and that was always, quite a nice mathematical expression. And now we are dealing with the logarithm of a sum. And that is one of the most ugliest things we can think of. Maybe you don't see it yet, but if you don't believe me, try to simplify this expression at home. And good luck with that. Oh, it's a very ugly log likelihood function. Actually, it's so ugly that it does not have a closed form solution. There does not exist such a thing. Very ugly. Very ugly. However, brilliant people out there, Dempster and his colleagues, had a good idea in 1977, and they said, let's introduce a set of indicator variables. And we've already seen those indicator variables earlier today, right? That is to say, Zii and ij indicates whether data point xj comes from cluster or Gaussian, in our case, I. These are the indicator variables we've seen earlier. And they are 0 or 1. And we can incorporate those into this probability, and that would then lead to a new likelihood function, which depends on the parameters theta we are interested in, the weights for those Gaussians and the mean vectors of those Gaussians. We have to extend this by this new set of latent, hidden, unknown parameters z. This is called the complete likelihood. And let's see what happens if we take the log of that. But before we do this, obviously I was ahead of myself, but here is a very crucial kicker, so I need to spend some time on that. These numbers are either 0 or 1. If they are 0, the contributing rest of this here will not contribute to this, the corresponding rest will not contribute to the value of that sum. It is zeroed out. Right? And also, they sum to 1, because we assume that every data point only comes exclusively from one Gaussian. It's not 2/3 from this one and 1/3 from the other. We roll a dice, say this data point will come from this cluster, and in this cluster it is somewhere over here. So we explicitly decide for a cluster. And that is to say, if we sum over all possible clusters, there will be an assignment of 0 to this cluster, an assignment of 0 to that cluster, an assignment of 1 to that cluster, an assignment of 0 to that, and so on and so forth. The sum over all the assignments to different clusters will be 1. Okay? So that boils down, and this is the brilliant idea here by Dempster and his colleagues, that a sum like this, where we have 0 or 1 here, can be expressed as a product like this, where these indicator variables are now in the exponent. Think of it. If this is 0, say for I equals 3, this is 0, then W3 and this here is 0. It will not contribute. In fact, the sum over this will only be the Wi and mu I where that thing is 1. Right? Otherwise, it does not contribute. Now, if this is 0, then if we raise anything to the power of 0, it will be 1. And from the point of view of a product, it does not contribute. And if it is 1, if we raise anything to the power of 1, it will be that anything. So because of these two crazy properties, this and this is the same. Sit down, look at this, think it through, convince yourself that this is true. This is something that does by no means whatsoever hold in general, but it holds for this and these conditions on these indicator variables. But then we can replace this ugly sum here that causes us this headache with this product. And that is to say, we now get this log likelihood, which now is really like a double sum. That this is now easy to be dealt with. A long story short, so this is the log likelihood of this Gaussian mixture with this Dempster trick. We can expand it into 3 terms. And of course, once again, this is the logarithm of a normal distribution. So this exponent of the normal comes down. This is e to the minus something. Logarithm of e to the minus is that minus something. Right? So 3 different terms, one with the weights, one with this normalization constant, one with the exponent here. I am not interested in these things because they do not say depend on mu. We happily ignore them for the time being. We are just interested in this term 3 here. Minimizing that thing, like the overall, we're interested in maximizing the overall likelihood, is to say that T1 plus T2 minus T3, so T1 plus T2 minus T3, this has to be as large as possible. But that is to say that like, you know, if we subtract something, then whatever we subtract should be as small as possible. Because if we subtract something large, then the overall thing cannot be large. We want to maximize something. So whatever we subtract has to be small, all right? Maximizing the likelihood implicitly means to minimize this term T3. And look at this. If we have this 1 over 2, I can pull that out. You know, can say that 2 times term 3 is this double sum Zij xj minus mu I squared. We have seen this before, haven't we? This is the objective function of k-means clustering. Exactly the objective function of k-means clustering. And that is to say that k-means clustering fits a Gaussian mixture model to the data. And in particular, it fits an extremely simplified Gaussian mixture model to the data. When you do k-means clustering, and it does not matter if you use Lloyd's algorithms or Hartigan's algorithm or McQueen's algorithm, what you do, you minimize this objective, and that is to say you do maximum likelihood fitting of a Gaussian mixture. And that Gaussian mixture is extremely simple because the covariance matrix for all the Gaussians is just the unit matrix. And therefore, as you said, it can only identify sort of circles rather than elongated structures. You have to know that k-means clustering can only work. Well, it will always work, but whether or not the results make sense depends on whether or not the data you apply it to consists of blob-like substructures. If that is the case, k-means clustering will do a beautiful job. If that is not the case, do not expect it to work well. Do not be such an idiot who downloads a library and applies it to whatever comes your way. Think about what you are doing before you are doing it. Can actually continue these proofs, can really make it precise that it will go for clusters of very small variance. The thing is, if the data you are dealing with does not consist of Gaussian blobs, then k-means clustering will produce results of questionable quality. That is the take-home message here. And for details, I want you to read these 2 things. All right, the first one actually discusses what we just discussed in detail, and the second one shows the second part of the argument. All right, I have more, but the construction side is turning up their activity, and we are almost done anyway. So I will not discuss this idea of soft k-means clustering. It's a shame, but it's not that important. Read this. I'll not discuss it because of the environmental conditions. So what we know about is the idea of k-means clustering. And again, it is by far the most popular approach towards grouping Euclidean vectors. Right? And we have seen that when we use this approach, in whatever form it comes, Lloyd's algorithm, Hartigan's algorithm, McQueen's algorithm, and there are even more, and one of them I dropped, what we are doing is Gaussian mixture modeling. And so k-means clustering should only be applied to data where you have reason to believe that it consists of local blobs, you know, some high dimensional space, 50,000 dimensions, whatever, like, you know, some blob over here, some blob over there. Then go ahead and use k-means clustering. However, if your data resides on crazy manifolds that are anything like, you know, long snake-like things and stuff like that, then do not be an idiot and use it. of course, the problem is you never know in advance, like because you have high dimensional data, you cannot plot it, you don't know in advance like how your data looks like. Try to visualize the data you're given to the extent possible, and then looking at some lower dimensional projections might already give you an indication of what you're dealing with, but do not apply it to non-Gaussian data. I mean, you can, but then you have to live with the consequences. And don't blame the algorithm. You have to blame yourself. And it was really baffling to me that professors who consider themselves experts in computational intelligence do not know this, and that turned me into an expert on k-means clustering. All the stuff I've written here is just sort of because, I need to get the message out. It's not the fault of the algorithm, it's the fault of the people who use it without consideration. Very important thing is also, and I have not proven that here, it is an extremely difficult problem. The algorithms are extremely simple, and this is why it's so popular, but they are but heuristics. This thing is NP hard. There's no guarantee for us to find the optimal solution. And the really, really, really crucial take-home message is that this is not k-means clustering. This is one way of how to accomplish it. Even though, honestly, I've checked Wikipedia, they now have mentioning of these two things without any details. But really, Lloyd's algorithm is how everybody does it. But this is how everybody should do it. For sure. All right? That is all I have got for today. Do you have any questions?
Professor, if these kind of problems come, like the one you said, does it make sense to change the distance function also to make it more...
What problem? I couldn't...
For example, one of the problems you showed where came in the detail to...
You mean this?
These kind of...
Yeah.
Maybe there could be other problems. Maybe your objects that we have not compared more have set-like structure. So then doing the Euclidean distance maybe not as good. Maybe doing the symmetric difference or something like that. So
what difference?
Symmetric difference of sets.
Symmetric. If you would have said Mahalanobis distance, I would have been very proud of you. Look, yes, of course, you are right. Right? We need a different idea for what it means to be similar. Euclidean distance to the mean of these clusters is not what would be appropriate here. There are distances, for instance, the Mahalanobis distance, that actually consider local covariances when they compute similarity. So yes, in that sense, if we were to replace the distance function, we could get a better result here. But replacing the distance function is to fit a more flexible Gaussian mixture model. So therefore, if you're dealing with data like that and want to identify substructures like these, then why use k-means clustering? Go for Gaussian mixture modeling right away. Right? And then it will identify the covariance, it will be much more computational demanding, but it will compute the mean and the corresponding covariances, and you get the clusters here. You had a question.
Yeah, I just wanted to get it clarified, or is it true that for all three algorithms, the number for k needs to be predetermined?
Oh, I never said that. Yes, right. Thank you very much. Yes, somebody has to provide k. Right? And I actually, oh my goodness. Thank you very much. Where does it come from? Nobody knows. Right? Here we look at it and say it must be 2. Or in this other example, we look at it and say it must be 3. In general, high dimensional data, lots of them, we don't know much about it. How do we choose k? Nobody knows. Right? We can run it with different choices for k. For every k, we run it 10 times, look for the best result. Then consider different k, run it 10 times, look for the best result, and we'll get some measure where it worked best. Like, okay, it seems as if these are 15 clusters in here rather than 5 or so. But there's also a very practical consideration. When we do clustering, what we are interested in is complexity reduction. Right? So if you do k-means clustering where k equals 1000, you're doing something wrong. So from a very practical point of view, and say you are a data scientist working somewhere, presenting your results to management and say, yeah, here's our customer database and we identified 1,230 different types of customers. What is the worth of that? Nothing. Right? So you have, this is our customer database and there are 4 types of customers in here. That is what managers can understand. So the choice of K is typically a very pragmatic one. And by pragmatic, I mean less than 10. All right? Yeah. But I should have mentioned it. Yes, this K has to be provided by yourself. It has to come from somewhere. You can try to estimate it automatically. It's a lengthy process and typically not worth it. Any other question? Okay, so they're turning up. Let's meet again this afternoon. Thank you.